Welcome. Well, and it's on the other side.
You need this stuff?
Just the microphone, I think. It's okay. I will just click. Thanks. Okay, thank you. I see we're running 15 minutes late. I'll try to be as fast as possible. Yeah, last famous word. No, I think it's because it's not super straight. Okay, so my name is Marco Scigliuzzo. I'm a postdoc in Tobias Kiefer group. But before diving into the experiment, I would like to join the previous speaker in thanking the organizer and congratulate for the choice of the venue. That is really great, as well as the conference. So I'm going to talk about quantum collective motion of macroscopic oscillator. And before going to detail, I want to tell you why I think mechanical oscillator are a really interesting object to study. So if you compare the speed of light to the speed of sound is much smaller, 5 orders of magnitude. Therefore, if you want to make a filter, you can have a filter with tiny footprint. Or in our phone, there are many mechanical filters. And now if you go to the quantum technology side, you can have atoms that it's to which footprint is really many order of magnitude larger than the wavelength of the photons that they interact with. So they're really giant atoms. Mechanical oscillator have mass. This means that you can make all kind of sensor and metrology of which mass is sensitive to. So you can make accelerometer, mass sensor, and of course, I guess you know that the detector for gravitational wave are indeed mechanical oscillator. But now we are able to couple this system to superconducting qubit and then encode a non-classical state in them. And of course, this is very important for metrology and sensing, and maybe in the future also for studying the quantum nature of gravitational field, and maybe detect possible kind of dark matter. And finally, phonons do not propagate in the vacuum, in the medium to propagate, so they have a very high Q, and that's why they're used in timing. And of course, in the quantum part, you can have quantum memories. There are different ways you can control a mechanical oscillator, but I'm going to concentrate on the optomechanical system. So if you consider just a optical cavity, a photonic cavity made of two mirrors, one in front of each other, you can have effectively one of the two mirrors mounted on an oscillator. So this mirror is free to move. So if you write now the Hamiltonian, sorry, my bad. If you now write the Hamiltonian, you can see that you have the two components, the photonic part and the mechanic part. But the frequency of the photons is modulated by the frequency of the mechanics. Therefore, you get an effective nonlinear parametric coupling between the photonic excitation and the mechanical excitation. So now if we drive the optical part and we concentrate on the vacuum fluctuation of the photonic component around the coherent state, we can go in the displaced rotating frame and basically getting this so-called linearized optomechanical interaction. And these give the ability to have different kind of interaction, because now if we drive on the red with the red detuned pump with respect of the mechanical microwave cavity or the optical cavity, we can have a beam splitter interaction. And at the same time, if we drive or excite the cavity on the blue, the tuned part, we will have a two-mode squeezing interaction. And optomechanical systems have indeed been used to realize ground state and strong coupling between microwave and or optics and mechanics. And indeed, as I showed before, driving on the blue part of the microwave cavity, also in getting squeezing and entanglement. And more recently are still reviving their interest for quantum transduction. But our platform is based on superconducting circuits. So where now you replace the optical cavity by an LC circuits. And in this LC circuit, you have a capacitor of which one of the parts of the plate that form the parallel plate capacitor is mechanically compliant. So it's basically free to oscillate. And the physics is exactly the same. You get this optomechanical interaction. And the system is very spread and has been very successful. And all the fabrication process relying on making thin superconductor membrane that have this kind of dome shape. But this is not ideal because when they are put in the cryogenic environment for being measured, the stress just get released and the membrane relax in such a way to minimize its stress. And this is very bad because you cannot control the mechanical frequency because, of course, you will have a relaxation depending on the fabrication process. As well, you don't control the microwave frequency. And this is hinder the scalability of the system. So we solved this problem by having a flat top. So I'm not going to go in detail for this presentation, but basically we have many benefits. So now our mechanical drum is has a tensile stress when cooled down cryogenic temperature, and this means that if you're familiar with the concept of dissipation dilution, more stress means more dissipation dilution. That means higher quality factor. At the same time, the gap size is controllable, meaning you have very precise and reproducible microwave frequency because your capacitor is always well defined. And at the same time, the mechanical frequency that is basically set by the diameter of this drum is very well reproducible. So we can make an LC resonator, as you can imagine, just shunting the our vacuum gap capacitor with an inductor. And these are microscopical objects. And the diameter of this is like close to a human hair, maybe not mine, but and this behave extremely well. You can excite the system and measure their ring down, and they will go on for 40 million of oscillation. So the quality factor is tens of millions. And we are able to cool down the system to their ground state. But even further, as I mentioned before, we can squeeze the system below vacuum and when we turn off the squeezing pump, we can track their dynamics and see that they remain squeezed below vacuum for 2 milliseconds. So this has been published last year. You can read the paper if you want to know the detail. But I mean, this talk, I want to mainly concentrate on the multimode optomechanical part. So there have been many theoretical proposals for multimode optomechanics, but the experiment almost completely limited to 2 modes. And usually these 2 modes are just ideally degenerate mode that get broken by some disorder introduced by fabrication. But with our technology, we are able indeed to extend the system to optomechanical lattices. And this work, again, has been published 2 years ago. And you can read the detail, but here basically you can use each mechanical system to probe the mode shape of this effectively strained graphene or minimal flake of strained graphene lattice. It's basically a 2D SSH if you want. But this concept is very general, so you can have any microwave mode coupled to each other. And now if you just go, I mean, in a simple diagonalization, you will have that each individual mechanical mode is going to have some participation ratio on the microwave mode. So just by measuring the relative participation ratio of the mechanical excitation on this particular microwave mode, you can actually reconstruct the mode shape of the system. So this is all nice, but what about in general collective system? So this is the experiment that I'm going to talk for the rest of the presentation. All the results are being uploaded last month on arXiv, if you're interested. And the concept is very simple. So we want to go from single mode optomechanic to having a single microwave mode that couple many mechanical oscillators. And now you can think if all these oscillators are resonant and in the presence of a red pump, you can indeed write the Hamiltonian as the following. And I guess you already recognize that the only mechanical mode that is coupled to the system is this particular bright collective mode. So effectively, in my system, it behaves as a single collective mechanical mode coupled to many other 5 dark collective mode. And this mode, this bright collective mode, indeed has this shape, and to help the intuition is just the one where all oscillator oscillate in phase. And I want to point your attention on the fact that now we have this an optomechanical enhancement due to the fact that we are coupled to many resonator at the same time. So this is in theory. In practice, even if the fabrication process is very good, we cannot exactly get resonant system. So of course, we will get many individual mechanical resonator trace. But remember, if we increase the red pump, we are basically increasing the line width of this mechanical resonator, because the total line width is given by the coherent intrinsic line width plus the optomechanical damping rate. And this is proportional to the photon number, meaning to the pump power photon number in the microwave cavity. So you can imagine that there is a region where this line width basically overcome the frequency disorder. And this is the one that we want to study. So this is the concept. This is our implementation. So we're not going to study a single microwave mode, like a single microwave resonator, but a mode of 6 couple microwave resonator. And I guess you can easily understand that there are 6 modes, and from symmetry, there are 2 pairs that are degenerate, but we are not interested in this mode. We want the one that have exact same participation ratio of the mechanics on the microwave. And these are just the 2 symmetric and antisymmetric mode. And in particular, because of the current inside the different modes, we can see that this antisymmetric mode is a dark mode with our waveguide, and the antisymmetric mode, and the symmetric mode is very broad. And this is very important because now we can use one mode for cooling or for controlling the system and the other for probing. So this is the system, and here I just show the microwave mode, and because of small frequency disorder in the fabrication, we can actually reconstruct exactly the mode shape. And the parameter are again extremely well controlled. As you can see, the mechanical frequency disorder is below 0.1%. And the quality factor of this system is in average above 12 million. That means they live longer than second time scale. The optomechanical coupling rate are just 10 Hz in this system, so we need to pump a lot. So in order to measure this system, you can imagine if we just send the coherent tone and see what gets scattered from the cavity, we will just see the Lorentzian shape of the cavity. But now let's suppose that we add a pump at the frequency read the tune equal to the mechanical frequency, and add this frequency to the coherent probe, we will see a transparency windows that opens in the system. So this is how we can get line width and frequency of the mechanical mode. And now, of course, I guess you already got the idea. If you have many mechanical mode, in this case, let's assume that they're not degenerate, you will see many spikes. So let's do the experiment. So here we do exactly optomechanical induced transparency. You initially see the cavity with all the mechanical mode. But now increasing the pump power, means increasing the intracavity photon number, we see different feature. So if you concentrate here, just a zoom of this region, we see that the line width of the mode, of the 6 mode increase. And then after a threshold, 5 modes appear with decreasing line width, with increasing pump power, and 1 mode disappear. And indeed, now if we look at this picture, we see that it disappear from the zoom in because it goes in strong coupling with the microwave mode. So if we collect all the measurement here, we see indeed that we can identify 3 regions. The first one, a low pump power, where each mechanical mode just behaves as standard single mode optomechanics. Their line will just increase. But then a second region where their line will start to increase, but then decrease. And then a third region where we indeed get strong coupling. And we can fit very well these 2 theory and extract the damping rate for the all modes line width, including the microwave cavity. And you see that again that these 3 regions are shown here. So at the beginning you get standard individual optomechanical system, but then at increasing cooperativity or equivalently photon number, we see that 5 modes start to become dark, and surprisingly, the harder you pump, the darker they become, their line will reduce, and then we have the appearance of this collective mode that now much larger damping rate. And in fact, pumping even stronger, we can get in the strong coupling between the microwave. So the microwave resonator or the microwave mode is strong coupling with the collective mechanical mode that is 3 orders of magnitude lower frequency. And indeed, this is much easier. It's much easier to see it in the frequency landscape. And we can introduce this collective enhancement factor just to have a way or a definition where we can see where this transition occurs. We can go further. We can measure the optomechanical mode shape. Indeed, if we now consider a pump, we can go in this strong coupling regime, and now we have all the different collective mechanical mode. And just by applying an excitation, we can excite this system. So all this system will just resonate as the collective mechanical mode. But then we can quench the coupling, meaning we just turn off the pump and let the system just evolve normally and collect all the oscillation. But since we know also the frequency of the uncoupled system, we can Fourier transform and measure the relative amplitude of each system and the relative phase. So we can indeed reconstruct the mechanical mode shape, both in amplitude and relative phase between different oscillators. And for the bright mode, this is the measurement, and below there is the theory. There is a almost perfect match. And we can do this for all the different dark modes. And as you see, there is a very good match between all dark modes and the microwave. Sorry, and the theory. Finally, we want to try to cool down the collective mechanical state. So here we're going to do a different measure than optomechanical induced transparency. We just turn on a pump and see the incoherent spectrum that come out from the sample. So it's important that we need to consider all added noise added in the microwave system by our amplification chain. And indeed, if we take everything into account, we can see that for increasing the pump strength, we get all the spectrum traces that fitted to theory, give us the effective occupation of the collective mechanical system. And we see that indeed we managed to pull down reasonably to the ground state, even though in this position we are limited by cavity heating. It's basically non-ideal behavior of our linear oscillator that just gets warm due to the thermal population due to the very high driving strengths. And finally, we want to show sideband asymmetry, meaning that when we pull down or we go in the collective regime with our pump, we can use our broad cavity as a probe. So just putting a probe at the frequency of the cavity, due to the different spectrum between positive and negative side of the frequency, we will have an asymmetry in the amplitude of the different bands. And we can do this measurement, indeed. In this part, we increase the pump strength, the cooperativity or the intracavity photon number equivalently, and we overlap the two bands just to make the asymmetry more visible. And if we extract the population from this measurement, we indeed see that we are well in agreement with the previous measurement just from calibrated spectrum that we took. And importantly, this is a calibration-free measurement. The asymmetry just comes from quantum mechanics law. So this was my last slide. I hope I convinced you that I'm very interested in this mechanical oscillator, especially with our new platform, because now we can indeed go in this lattice or this more scalable system. We did the first step towards quantum collective optomechanics. We prepared this the ground state of the collective system, and now we are already making new design to get collective mechanical state squeezed below vacuum. And we are also interested to see in this system non-Hermitian dynamics and possible entanglement between different mechanical resonators. So with this, I want to thank you for all the attention, all the funding agency, because these experiments are quite expensive, and all the group that were involved in the experiment. So thank you.
Is there an application reason for adding that for resonator?
So you have, depends what you define as application. So ideally, you can do metrology and sensing, because now you have a distributed quantum state. So for example, I mean, this is very far-fetched, but let's say that you want to study some gravity decoherence, gravity-induced decoherence. So now your length, your extension is much larger, and this is one of the two players. One is the effective mass of the system, and the other is the effective distance. And so this can be one thing, or you can do maybe sensing on a delocalized manner. But again, if this is a real application or still on more scientific interest, it's debatable. Yeah.
You're driving the system in modes. What do you mean by configuration of the ground state?
So basically, yeah, maybe it's okay. So this is, you are just driving on the red side band of one of the microwave modes. And this microwave mode is equally coupled to all the mechanics. So basically, you're just having a beam splitter interaction between a very cold cavity and the mode that is mechanical mode that is collective, that is warm. So you increase the interaction strength because of the nonlinear interaction of the optomechanical part. Basically, you are thermalizing the mechanics to the microwave mode. And since these are 5 gigahertz and we put in the dilution refrigerator, they are in the ground state just by normal relaxation. Yes, this is the option. Of course, since we really need to drive at very large number of photons, we have like nonlinearities in the system. You see, I mean, the number of photons in the cavity can be extremely large. So small amount of this photon can basically get like converted in thermal excitation, the incoherent excitation that basically limit the cool down, the ground state that you can prepare. If the cavity was colder and there is enough coupling, you can get like, I don't know, 99% or 99.9% fidelity. Here is just 60%.
before you enjoy the last workshop about the